sound, can make light. Not as a metaphor, an actual flash you can measure. A single trapped bubble in water breathes to an ultrasonic beat, and then at the same point every cycle it blinks. If sound is just vibration, where do the photons come from? There's a real laboratory effect with an almost embarrassing name, sonoluminescence, sono for sound, luminescence for light. Put together it says something your brain refuses to believe. Sound makes light. Not metaphorical light, not it heats up and glows a little, real measurable flashes. You can catch them with a photomultiplier tube, you can time them, you can analyze their spectrum. And the strangest part is how clean the setup can be. A container of liquid, usually water, sometimes sulfuric acid, sometimes glycerin, a sound source strong enough to shake the fluid, typically an ultrasonic transducer glued to the container, so the whole thing becomes an acoustic resonator. And then under the right conditions you trap a single microscopic bubble in the standing sound wave, and that bubble starts doing something like breathing. It expands as the pressure drops, it collapses as the pressure rises, over and over, thousands of times per second. And at the moment of collapse, right at the end of that squeeze, there's a flash, a tiny blink of light, often so short it's hard to even wrap your mind around the duration, tens to hundreds of picoseconds. That's a time scale where light itself only travels a few centimeters while the flash is happening. So now we have a physics problem that sounds like science fiction but isn't. We're not asking, does it happen? It happens. We're asking the more annoying question, if sound is just vibration, where do the photons come from? Because sound, as you normally meet it, doesn't look like the kind of thing that should ever create light. Sound is pressure variations in a medium, a mechanical wave. If I play a bass note through a speaker, the air jiggles. If I send ultrasound through water, the water jiggles. Nothing about that picture screams visible radiation. Light is electromagnetic, its charges accelerating, fields oscillating, photons being emitted. In most everyday situations, to get visible light, you either heat something up until it glows, incandescence, minus do chemistry that ends in an excited molecule, chemiluminescence, run electricity through a gas, a discharge plasma, or drive a semiconductor LED. None of those are sound. So the first job is to stop treating sound as some weak, gentle thing. Sound is only quiet because you're used to small amplitudes. The key knob in this experiment is not frequency, it's pressure, amplitude, A strong acoustic field in a liquid can swing the pressure by multiple atmospheres. That's not a vibration you feel in your eardrum. That's a moving landscape of high pressure and low pressure that can rip the liquid locally into tiny voids. Those voids are bubbles, cavitation bubbles. Cavitation is already a clue that we're not in the normal world anymore. A liquid usually hates to have empty space inside it. So when a bubble forms and grows, the surrounding liquid is pulled apart. When the pressure reverses, the liquid rushes back in to fill the void. And liquids can rush in fast because liquids are heavy and stubborn. They don't compress much, so when they move with force. Now most cavitation is messy. Lots of bubbles, random sizes, turbulent collapse, noise, erosion, damage to propellers. Sonoluminescence has a messy version, too many bubbles collapsing everywhere, producing a faint glow. But the shocker is the clean version. Single bubble sonoluminescence, In that version you can literally trap one bubble in the pressure node of a standing wave. The sound field acts like a kind of invisible egg carton. The bubble sits in a stable spot. It doesn't rise like a normal bubble because buoyancy is fighting a dynamic pressure gradient that pins it in place. Then you tune conditions so it doesn't just dissolve away or explode into many bubbles. That tuning depends on gas content in the liquid, dissolved air, temperature, the exact driving frequency, and sometimes adding a noble gas like argon to stabilize the behavior. Once it locks in, it becomes almost like a clock. Every cycle of the sound wave, the bubble goes through expansion and collapse. And on each collapse flash, you can measure that the flash timing is phase-locked to the drive. That alone is unsettling. It means this is not random sparks. It's a repeatable, deterministic conversion of mechanical energy into electromagnetic emission. Nature is doing it on schedule. So where is the energy stored? Not in some mysterious new field. The energy is in the acoustic wave you're driving into the liquid. You pump mechanical energy into the system continuously. The bubble is acting like a converter. But that doesn't solve the real mystery. It just moves it. How can a gentle macroscopic pressure wave concentrate its energy into a microscopic region enough to produce light? because a photon in visible light has an energy of a few electron volts. To get visible emission by heating, you typically need temperatures of thousands of Kelvin. To get a spectrum that looks hotter, you may need tens of thousands of Kelvin. Some analyses of sonoluminescence suggest effective temperatures far higher, though temperature here is slippery because the system is tiny and far from equilibrium. Still, regardless of how you argue about temperature, you cannot escape the basic point. The bubble interior is for an instant in an extreme state, something like a microstar event happening in a glass of liquid. And that's why this is a good physics problem. It forces you to confront two big ideas at the same time. One, energy focusing, how a distributed low-grade disturbance can focus into a violent high-grade event. 2, mechanism of light emission, what physical process inside that collapsing bubble actually produces photons. If you ask 10 scientists for the one-sentence explanation, you'll get something like, the bubble collapses, compresses the gas, heats it up, and it emits light. That's not wrong, but it hides the real questions under a rug. Because compression heating is easy to say and hard to earn, you have to show that the collapse is fast enough, symmetric enough, and intense enough. You have to deal with the fact that the bubble is not a rigid piston cylinder. It's a deforming interface with surface tension. The gas inside can exchange material with the liquid. The collapse can generate shock waves, chemical reactions can happen, ionization can happen, water vapor can rush in and then get squashed. Even the presence of a tiny amount of noble gas changes the stability and brightness dramatically. And then there's the most irritating part, the part that makes it exciting and not just a solved textbook exercise. We still don't fully agree on the detailed story. We have strong models. We have fluid dynamics equations that predict a violent collapse. We have evidence that the bubble wall reaches enormous velocities. We have estimates of peak pressures and temperatures that are astonishing. We have spectral measurements showing broadband light, often without sharp lines, suggesting something like thermal emission or bremsstrahlung from a hot plasma. But details keep slipping through your fingers. Exactly how the energy partitions. Exactly how ionization starts. Exactly why the pulse is so short. Exactly what the spectrum is really telling you. Whether the interior behaves like a tiny blackbody radiator, or a non-equilibrium plasma, or something in between. And how the chemistry of the bubble contents affects the emission. So the problem statement of this whole story is simple to say, but not simple to answer. A sound field in a liquid drives a microscopic bubble into oscillation. At collapse, the bubble emits a pulse of light. The emitted light is synchronized with the sound. The system is macroscopic, but the emission is microscopic and extreme. What is the physical chain from pressure wave to photons? Hold on to that. Because if we can explain this honestly without magic words, you'll get something valuable, a new sense of what everyday physics can hide. A glass of water can contain conditions that, for a fraction of a nanosecond, resemble the violent environments we normally reserve for stars and shock tubes. Next, we're going to build the chain step by step, how a standing sound wave can trap a bubble, how the bubble can behave like an energy-focusing lens, and why collapse is not a gentle shrinking but a runaway implosion. And then we'll face the uncomfortable part where the explanation is solid and where it still has teeth. So let's earn that collapse. No slogans. First, the trap. If you drive a container of liquid at ultrasonic frequency, you don't just get sound moving through water. You can get a standing wave, a stationary pattern of pressure nodes and antinodes, like a guitar string but in 3 dimensions. At certain spots, the pressure oscillation is strong. At other spots, it's weak. A bubble in a sound field doesn't behave like a dust speck in air. A bubble is compressible. It changes size with pressure. That means the sound field can push it toward particular regions, because the bubble effectively samples the pressure gradient over a cycle. The net result is called the primary Bjerknes force, an average force that can pull the bubble toward a pressure antinode or node depending on its phase response. In single bubble sonoluminescence, you tune things so the bubble sits stably at a point in the standing wave. It's not drifting up. It's not crashing into the wall. It's pinned by the acoustic field. Now the breathing. The simplest picture is pressure outside the bubble goes up and down. The bubble radius responds, but you quickly learn the bubble is a dynamical system with inertia. The liquid has mass. When the bubble expands, it has to push liquid out of the way. When it collapses, the liquid has to rush back in. That rushing liquid has momentum, and momentum doesn't stop politely when the external pressure turns around. The classic equation people use as a starting point is the Rayleigh-Plesset equation, which is basically Newton's second law for a spherical bubble wall in a liquid. Pressure difference drives acceleration of the wall, with terms for surface tension, viscosity, and the inertia of the surrounding liquid. You don't need to memorize the equation, you need to feel what it implies. Minus, when the external pressure drops, the bubble expands. Expansion can be relatively slow. Then, when pressure rises again, the liquid doesn't just push the bubble smaller. The liquid ** falls inward, ** like gravity pulling a collapsing roof. Here's the key asymmetry. The bubble can expand to many times its minimum radius during the low-pressure part of the cycle, storing energy in the motion of the surrounding liquid and in the compression state of the gas. Then the collapse happens in a much shorter time, and the energy gets concentrated. Energy focusing is the whole trick. The sound field supplies energy on the scale of the container. The bubble converts it into a tiny event by acting as a kind of asterisk, acoustic capacitor, It slowly charges during expansion and then discharges violently during collapse. Now imagine the bubble at maximum expansion. It might be tens of micrometers in radius. That's still microscopic, but it's huge compared to its minimum radius, which can be sub-micrometer. During collapse, the radius can shrink by a factor of 10, 20, even more. Volume scales as radius cubed, so a factor of 20 in radius is a factor of 8,000 in volume. Whatever gas and vapor is inside is being squeezed into a space thousands of times smaller. If the collapse is fast enough that heat doesn't have time to leave, approximately *** adiabatic *** compression, then squeezing raises temperature dramatically. That's not a cute theory, it's the same reason a bicycle pump gets warm. The difference is that a bike pump is slow and leaky compared to a bubble collapse. If you take an ideal gas and compress it adiabatically, temperature scales roughly like a power of the compression ratio. With extreme compression, you get extreme temperatures. Even with conservative assumptions, you get thousands of Kelvin. Under stronger assumptions and faster collapse, you can get much higher. But there's a catch. Two catches, actually. Catch number one, the bubble is not filled with dry gas. It contains ** water vapor, **, and vapor changes the story. Water vapor can condense during collapse, releasing latent heat. Also, vapor molecules can absorb energy in internal modes. They can dissociate, they can participate in chemical reactions. All of that changes how hot the gas gets and how it emits light. Catch number two, at high collapse speeds, the gas might not remain a gentle, uniform, compressible fluid. You can form an internal *** shockwave *** in the bubble. The compression can steepen into something like a miniature blast wave that focuses toward the center. That's a whole other level of concentration, not just the bubble wall moving inward, but a shock converging to a point. A converging shock is one of the nastiest devices nature has for creating extreme conditions. It's the same idea used in inertial confinement fusion. Take a spherical shell, drive it inward, and let geometry do the work. A sphere is an unfair advantage. Everything points to the center. So when people say the bubble collapses and gets hot, the honest translation is ***. The bubble collapse is an implosion problem. ***, and geometry can make implosions brutal. Now you might ask, if it's that brutal, why doesn't it just destroy the bubble instantly? Because the bubble isn't a one-time event. It's a driven oscillator that reaches a kind of steady state. And steady state here doesn't mean gentle. It means repeatable. The stability depends strongly on the gas content. If the liquid is full of dissolved air, bubbles tend to grow uncontrollably and then break apart into cloud cavitation. If the liquid is too degassed, the bubble can dissolve away. In the sweet spot, something subtle happens called *** rectified diffusion, ***. During expansion, the bubble has a larger surface area and lower internal pressure, so gas diffuses into it more easily. During collapse, the area shrinks and pressure rises, so gas diffuses out less effectively. Over many cycles, this can create a net influx of gas, allowing the bubble to maintain itself. But then why doesn't it just keep growing? Because other effects balance it. Gas diffusion, chemical reactions, the dynamics of the oscillation itself. In practice, experimenters adjust dissolved gas concentration and often include a noble gas like argon. Argon doesn't react chemically and it has different thermal properties. It tends to help produce a stable, bright sonoluminescing bubble. Now we're ready for the moment of truth, the flash. Suppose for an instant the gas inside becomes extremely hot and dense. What emits light? Several mechanisms are on the table, and different experiments emphasize different aspects. One, ***, thermal emission ***. If the interior behaves roughly like a hot radiator, you get a broad spectrum. Many measurements show broadband light that can look approximately blackbody-like, though interpreting it is tricky because the system is tiny and the light must pass through the bubble and liquid. 2. Bremsstrahlung, if the interior becomes a plasma, electrons and ions, then electrons decelerating in the fields of ions emit radiation. That also tends to be broadband. 3. Recombination, radiation, and molecular emission. If molecules dissociate and then recombine, or if specific excited states form, you can get line features. Sometimes lines are weak or absent in typical single-bubble sonoluminescence, which is part of why people lean toward plasma-like broadband processes. Notice something: none of these require sound turning into photons directly. Sound supplies mechanical energy. The bubble collapse concentrates that energy into heat and ionization in a very small region. Then ordinary electrodynamics takes over. Hot charges radiate, excited states decay, photons leave. So the conversion chain is plausible, but plausible isn't satisfying, because you still want to know, is the energy budget even in the right ballpark? It is. The emitted light energy per flash is tiny, often on the order of picojoules or less. The acoustic power you drive into the resonator can be orders of magnitude larger. Most of the energy goes into heating the liquid, generating sound, and sustaining the oscillation. Only a tiny fraction emerges as light. That's an important psychological point. You're not getting free energy. You're watching a spectacularly efficient focusing of energy in space and time, not a large extraction of power. And now the detail that makes the whole thing feel unreal. The flash is ridiculously short and phase-locked. That suggests the emission happens at a very specific stage of collapse, likely when density and temperature peak, possibly when a shock converges or rebounds. So here's where we stand at the end of this section. Minus a standing sound wave can trap a single bubble. The bubble undergoes large amplitude oscillations. Minus a collapse is inertial and can be violent, potentially shock-driven. Minus a collapse is inertial. Karbutstabarchen sorda. Karbutstabarchen temperatures. Karbutstabarchen temperature recharts. 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 But we still haven't confronted the fragile part of the story. What extreme really means here, what sets the maximum, and why the details like gas-type dissolved content and even tiny impurities change everything. That's where it gets delicious. Because the bubble is small enough that chemistry, fluid mechanics, and electromagnetism all collide in one place, and nature doesn't promise to separate them neatly for us. Next, we're going to zoom in on the collapse itself. What limits symmetry, what makes the flash so consistent, and why the experiment is both beautifully explainable and still in some corners genuinely mysterious. Zoom in tighter, because the whole show lives in the last microsecond. A collapsing bubble sounds like a simple sphere shrinking, but a sphere is an ideal. Real bubbles get deformed. If the collapse becomes lopsided, you don't get a clean focus into the center. You get a jet liquid spearing through the bubble like a microscopic dagger. That's what causes cavitation damage on propellers. Asymmetric collapse near a surface makes a high-speed jet that slams into metal. Single-bubble sonoluminescence only works when you keep the collapse remarkably symmetric That's why the bubble is held away from walls, why the acoustic field is carefully tuned, and why the bubble size is controlled. The geometry has to stay round enough long enough for the implosion to focus. So the experiment is a balancing act, minus big expansion to store energy, minus violent collapse to concentrate energy, but not so violent or distorted that the bubble breaks or jets. And you see that balance in the data. Change the driving pressure a little, and the bubble stops glowing. Change the dissolved gas content, and the glow changes intensity or becomes unstable. Add a bit of argon, and the light often becomes stronger and more stable. It's like you're tuning a musical instrument that plays not sound, but temperature. Now, how hot does it get? If you read popular descriptions, you'll see numbers thrown around, 10,000 K, 100,000 K, even millions. The honest answer is we have estimates, and the estimates depend on models and assumptions, because measuring the interior state directly is brutally hard. You can't stick a thermometer in a micrometer bubble that collapses in nanoseconds. What you can do is measure the emitted spectrum, the pulse width, and the dynamics of the bubble radius. often with fast imaging or light scattering. Then you fit models, adiabatic compression, shock formation, plasma emission mechanisms, chemical kinetics. What's solid is this: the conditions at collapse are extreme enough to produce ionization and broadband emission. That means we are not talking about warm water. We are talking about a transient state where ordinary molecular comfort breaks down. But here's the part that keeps the mystery alive. Different models can reproduce parts of the observations while disagreeing about the details. One model says, mostly adiabatic heating of a noble gas core, leading to plasma and bremsstrahlung. Another says, shock focusing is essential to reach the observed pulse widths and intensities. Another emphasizes chemistry, dissociation of water vapor and subsequent reactions, alter the energy partition and emission. And there are debates about whether the spectrum is truly thermal or whether it only looks thermal because many non-thermal processes add up to something smooth. So the phenomenon sits in a sweet spot between understood and not settled. And that is a very scientific place to be, by the way. People sometimes think science only has two boxes, known and unknown. Real research lives in the middle box, known enough to predict and reproduce, unknown enough to argue honestly. Now step back and ask what we've actually done. We started with a macroscopic thing, sound pressure in a container, a wave you can generate with electronics, something you could almost think of as harmless vibration. And then because of geometry and nonlinearity, that wave creates a recurring microscopic catastrophe, a bubble imploding, compressing gas so fast that it creates a flash of light. This is not sound magically turning into light. It's more interesting than magic. It's asterisk energy being focused by dynamics. You can in principle calculate, and that's the unsettling lesson. The universe has tricks for concentrating gentle inputs into violent outputs, not by breaking laws, by using them. A bubble is a lens, not for light, for energy. Now the existential payoff, because you deserve one. When you look at a glass of water, you see calmness, transparency, nothing happening. But the calmness is a lie your senses tell you because you're too big and too slow. Inside that liquid, pressures can swing, cavitation can occur. If you drive it the right way, you can make the water perform something like a tiny stellar act, compress, heat, emit. A star shines because gravity compresses gas until it's hot enough to radiate and fuse. Sonoluminescence shines, briefly, because sound compresses gas until it's hot enough to radiate. Different engine. Same basic idea. Compression creates temperature. Temperature makes light. And that should change the way you label the world. Everyday, cosmic, mundane, extreme. Those are not categories nature respects. They're categories your nervous system invented so you could find food and avoid cliffs. Physics doesn't care about your categories. Physics cares about scales and mechanisms and constraints. Give it a way to focus energy and it will do it quietly, reliably, with no drama. That's why sonoluminescence is such a perfect topic for this channel. It's not a trick. It's not an illusion. It's a reminder that the deepest phenomena often hide inside ordinary materials, waiting for a clever way to be asked. And there's another angle that's even more human. Think about how we treat mystery in modern life. We usually mean something supernatural or unknowable. But sonoluminescence is a different kind of mystery, a phenomenon you can reproduce on a benchtop, with ordinary matter obeying known laws, yet still complicated enough that the last pieces of the story aren't agreed on. That's not a failure of science. That's the frontier. The bubble is small, fast, violent, chemically active, and strongly coupled to the surrounding fluid. It's a perfect storm for complexity. So if you felt a little discomfort when you heard sound makes light, good. That discomfort is your intuition realizing it has been living off simplified cartoons. Here's what I want you to walk away with. Not wow, weird experiment, something sharper. Sound is mechanical energy. It can be strong. A bubble is not just a bubble. It's a dynamic system with inertia and geometry. Collapse can focus energy into a microscopic region. Focused energy can produce states of matter that emit light. And the world you call quiet is full of sleeping extremes. If you want a single image to keep, picture a tiny bubble suspended in a pressure wave collapsing like a miniature universe crunch, then blinking over and over like a heartbeat made of light. If you're the kind of person who likes physics not as homework but as a way to see reality with new eyes, stay with me. Because once you accept that a sound wave can set off a light flash in water, you're ready for the bigger theme behind it. How the universe hides enormous violence inside gentle appearances, and how we can uncover it with nothing more than clear thinking and careful experiments.